Alrighty, my people. Hope we're doing well. This is going to be several different examples of sine and cosine graphs. I'm going to be working off of an old worksheet that I gave my honors pre-calc kids many years ago, mainly because they're already written, because the problems are already written. Now, the ones that I'm highlighting are the ones that are going to be covered in this video, and if we need to, then another video. I'm going to go ahead and read off the instructions, though. I mean, first of all, we need to list any and all transformations that the given function represents. Okay. This next part is not something that you are responsible for the quiz, but seeing as the entire purpose of doing summer trig is to get you all up to speed so that the trig is not a limiting factor when you get to learning the calculus, I am going to go ahead and do those steps. I may not do it in that order, but I will be using inverse trig to determine the location of max and min points, and perhaps the x-intercept, unless it takes us too long. But I do at least want to sort of introduce this. Then we'll graph the function, and then of course, as is with every graphing, assignment, you need to use your graphing calculator to confirm your graph. And we may do that on some of these, but of course that's mainly so that if there's no answer key to the worksheet that is given for the graphing one, you have recourse to figure it out from there. Okay. Let's go ahead and let's do our first function. We know f of x is equal to -2 sine x minus pi over 2 plus 1. Okay. Now, let's stop for a second and let's consider how many transformations there are. And if you said 4, you're right. Okay. The first one is here. This represents the second and the third one, because despite the fact that that is a single number, there are two aspects to it, right? We will be dealing with its negativeness and its 2-ness, and that right there is our fourth one in terms of the order of operations. So I know that my transformation is going to take me to the right, pi over 2. I'm going to have an x-axis reflection, that's the negativeness of your a value. I'm going to have a vertical stretch of 2, that's the 2-ness of your a value, and then we're going to move up 1 unit. Now, as I've said before, in order to actually determine the scaling on the graph, it's probably a good idea to determine where the maximum and minimum points are going to be. And you should be able to discern that because you know that your axis of oscillation, which on the parent function is just the x-axis, your axis of oscillation is y is equal to d. Well, in this case, d is 1. Okay. Now, you know that your amplitude, meaning how far the sine or the cosine graph will stretch up from that axis of oscillation, is determined by the absolute value of a, by the magnitude of a, its 2-ness, okay? And so you know your max is going to be d plus the absolute value of a, which in this case is 3. And you know your min values are going to be d minus the absolute value of a, and in this case that's going to be -1. And that shouldn't surprise us. Basically, the whole thing is going to move up, and then it's going to stretch away from this y is equal to 1. But I need to know these values so I don't make a boneheaded move when it comes to trying to figure out the scaling. So let's go ahead and let's do it this way. Let's go ahead and say every y is 3 units, right? So this is 3. This is 2, this is 1, that's 0, that's -1, -2, and -3. That doesn't give us a ton of room, but I don't want to leave myself too much room because then the graph is itty-bitty. I want to see the graph, but I don't want to make it so big that it pushes part of the graph off the Cartesian plane. Now, there is no change in period. That means that the usual scaling that I use in terms of pi 2 pi, and 3 pi will probably be sufficient. That's negative pi, that's negative 2 pi, and that's negative 3 pi. Alrighty, well, let's go ahead and draw the parent. Okay, the parent is, starts here. It goes up to here, comes down, drops down to here, goes up to here, drops down. Okay, and we know that, at pi over 6, it's 1/2, and so we can kind of put these points in here to make sure that we don't mess up the graph too much when we're sketching it. It's not absolutely pivotal that it be perfect, but we do want our graph of the parent function to be able to guide us in our transformation. Sorry, in order to get this graph the least bit respectable, I'm going to have to turn this real quick, and I'll turn it back here in just a second. Okay, there is our sine graph. Now let's go ahead and draw this y is equal to d line. Okay, because I know that as an axis of oscillation, just kind of like horizontal asymptotes or other end behavior asymptotes, it's nice just to have this dashed line on here as a guide for us. Okay, let's go ahead and take this this intersection point right here at the origin, and let's transform it first. It goes pi over 2 to the right. Then it's going to x-axis reflect and vertically stretch. Now, it's at the 0 value for y, and you can't stretch or reflect 0, so it basically stays there, and then it moves up 1. Okay, now I know that there has not been a change in the period, which tells me that there's still going to be maximums at the same interval, minimums at the same interval, and the graph is going to intersect the axis of oscillation at the same interval. Now in the parent function, the period is 2 pi, and notice I have 2 points of intersection per period. And so I'm going to have the same here. And so we're just going to, go pi over, we're going to go pi, and then another pi, and then negative pi, and negative pi, and negative pi, and that is going to basically be our points of intersection of this axis of oscillation for our function. Now let's transform this maximum value right here on the red. I'm not pointing to the axis of oscillation intersection that I just plotted. I'm the red point underneath. Okay, let's move it over to the right, pi over 2. Then we're going to x-axis reflect it, and we're going to vertically stretch it by 2. So x-axis reflect from positive 1 to negative 1, vertically stretch negative 1 to negative 2, and then I'm going to move it up 1 unit. And boom. That is going to be one of my minimum points. Well, remember that I have not changed the period. My minimum points should be on the same consistent interval all the way off to positive and negative infinity. Now in the original, maximums and minimums are 2 pi apart. So if I'm at pi, then 2 pi to the left, another 2 pi to the left, and 2 pi to the right gives me my minimum values. Now let's take this minimum value, let's take this minimum value and let's transform it. Move it to the right, pi over 2. Okay, now I'm going to x-axis reflect it, and then I'm going to stretch it, and then I'm going to move it up 1. And here is my maximum value now. And again, I know that it happens every 2 pi, and so there you go. Now, though these points are getting pretty far apart, so it's probably a pretty good idea to go ahead and transform that bad boy right there, that pi over 6 1/2 value. Now pi over 6, when I move it to the right, pi over 2, I'm moving it to the right 3 pi over 6. So pi over 6 and 3 pi over 6 is 4 pi over 6, or 2 pi over 3, which is right here. Then I'm going to x-axis reflect it. Then I'm going to stretch it from negative 1/2 to negative 1, and then I'm going to move it up 1. And here I go. Now that right there means that that point right there on that negative hump is also a relevant point. And if I'm sort of mirroring it in terms of the symmetry to the positive humps, to the maximums, I can go ahead and put those there. Boom, 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 and boom, boom. There we go. Now, that means that my graph should look something like this. Okay, that's a pretty graph. Okay, now let's go ahead and let's use some of the analytic tools in order to discern exactly what's going on here. Now, the function as it was given was f of x is equal to -2 sine x minus pi over 2 plus 1. Now let's say that I wanted to find my maximum values, okay? My maximum values, I've already figured out we're going to be at 3. So remember that anytime you're given a function, you can ask that function questions. And you can say, Mr. Function, at what x value are you going to have an f of x value of 3? Okay. And then in order to answer that, you simply have to do the algebraic work. So we, of course, in terms of solving an equation, we just simply want to undo the things that have been done to the variable, and we want to undo them in the opposite order in which they have been done, right? So we're sort of undoing we're going from the outside in and undoing the order of operations. Now, this means that I have x minus pi over 2 is equal to the arcsine of -1. Now, we will get to talking about inverse trigonometric functions, but here I'm merely using inverse trig as an operation. And what this is asking is, for what angle measurement is arcsine equal to, is your sine ratio equal to -1? And well, we know that sine is -1 at 3 pi over 2, right? At 3 pi over 2. Now, okay, but it's not just at 3 pi over 2. It's at every coterminal of 3 pi over 2. And so we're going to express that as 2 pi n, where n is understood. Oh, sorry, that should be still pi over 2. Where n is understood as every integer, okay? So it's 3 pi over 2 plus 2 pi times 1 plus 2 pi times 2 times 3 times 4, and then also times -1, -2, -3, -4. Obviously, when n is equal to 0, 3 pi over 2 is just 3 pi over 2. But this is the way that you represent that the answer to that question is not one value, but an infinite number of values because of the periodic nature of the function. And so what we get here is we get maximum values, okay, at pi plus 2 pi n. Okay. Oh, now the problem with that is when I add pi over 2 to 3 pi over 2, it should be 2 pi. Sorry, I was trying to figure out why in the world it didn't make sense. So basically, this tells me that my maximum values, which give me an output of 3, happen when x is 2 pi or 2 pi before or after that, which of course includes 0. And that we see. We see it at 2 pi. We see it at 2 pi minus 2 pi, 2 pi minus 4 pi, and then it'll be at every 2 pi before and after that all the way along. Okay. Now the minimum would be exactly the same, but let's go ahead and see if I can use my analytic skills to go ahead and find, Mr. Function, where are you 0? All right. Well, that's going to be a little more difficult, and we'll see why here in just a moment. And so we're going to use our algebra skills to get down to the fact that we're asking where the sine ratio is equal to 1/2. Now, on the unit circle, sine is equal to -1 at only one place. Sine is equal to 1/2 at 2 places. Okay, it is equal to 1/2 at pi over 6. Okay, so x minus pi over 2 at pi over, if I could actually talk and write at the same time, at pi over 6, and at 5 pi over 6. Okay, but of course it's not just at pi over 6 that sine is 1/2. It's pi over 6 plus 2 pi n, and it's 5 pi over 6 plus 2 pi n. Now I've left this open right here because when you add pi over 2 to pi over 6, and we've already done this, you're going to get 2 pi over 3, right? Because this is 3 pi over 6, adding to 1 pi over 6, which is 4 pi over 6, and we're going to get 2 pi over 3 plus 2 pi n. This over here is going to be 3 pi over 6 plus 5 pi over 6, which is 8 pi over 6, which reduces to 4 pi over 3 plus 2 pi n. And what I get here is I get 2 answers for when I'm going to get zeros. Okay. Now that shows us, and they're not evenly distributed because I'm looking at where there's 0, 2 pi over 3 and 4 pi over 3. But notice that 6 pi over 3 there isn't a 0, right? Because it's shifted up, those aren't, like, you don't have the same distance between these two as you do between these two, so they need to be characterized differently. You get 2 pi over 3 plus or minus 2 pi n, and you get 4 pi over 3 plus or minus 2 pi n. Okay, and that's how you can use your analytic to reinforce your understanding of the graphical, the geometric, or you can use your geometric to reinforce your analytic, your notational understanding of what's going on. And that's always a good thing, to have those multiple perspectives on the whole. It allows us to be a little bit more confident in exactly what it is that we are trying to communicate, right? Okay, well, that took me much longer than I expected. Let's go ahead and do the next one. I think we'll probably skip the analytic work on the next one, and we'll just do the transformation. Okay. Now, this next function is f of x, or actually it says g of x, but whatever, cosine of -1/2 x plus pi over 4. Now we need to be very careful, because factoring out a fraction, sometimes our wires get crossed, and since multiplication and division are basically the same operation, it becomes a little bit difficult sometimes. Obviously, if I want to take a -1/2 out of the first term, x is left over. If I want to take -1/2 out of pi over 4, what times -1/2 will give you positive pi over 4? And it's -pi over 2, right? And remember, you ask yourself that question because factoring is a form of division, okay? Now, since cosine is even, that negative is nullified. It doesn't really matter, okay? And at this point now, whereas there looked like 3 transformations, we now see that there are only 2. We're going to move to the right pi over 2, and we're going to horizontally stretch by a factor of 2. And remember that both of those behave quote-unquote opposite. because they're based on the logic of compensation. X needs to be pi over 2 units larger to compensate for the minus pi over 2. This value right here needs to be twice as large to compensate for the 1/2 and get the same output, okay? So let's go ahead and let's make our, let's change the scale since we're going to be horizontally stretching. Okay, and we'll go for a scale that is half as big as the original. Now, there's not going to be a vertical change in shape, so we can be a little bit more aggressive with how we scale the y, and we can do, you know, -2.5 to +2.5. Now let's go ahead and do our our parent function. We know that cosine starts up here, and we know that it comes down to here at pi over 2 and gets to its minimum at pi and comes back up to the axis at 3 pi over 2. And of course, since it's even, we're going to have exactly the same behavior over here. And there you go, okay? And you know that, you know, at pi over 3, you're going to get 1/2, and so we can kind of use those values to round out a little bit more and give ourselves a nice, clean and smooth and accurate curve, okay? Okay, there is our parent. Now, what we want to do is we want to take some of the representative points, transform them, and then use the symmetry in the period in order to extrapolate the other points from there. So we're going to take 0, 1, we're going to move it over pi over 2, and then we're going to horizontally stretch it by 2. But remember, you horizontally stretch from 0, and this right here, this x is equal to c line, is our new 0 point. So the moment that we move over, you can't stretch 0, so it just goes right there. Now, you have horizontally stretched it, so you know that your maximums are going to be, yeah, oh gosh, I totally messed up that scaling. I should have gone the other way, but let's not worry about that right now. I'll just do too little of the graph. It should have been 2 pi and 4 pi and whatever. Because we're stretching it, we need to see more rather than less. But so what we have here is we have this maximum right here. So let's go ahead and move this 0 point, this x-intercept. We're going to move it to the right pi over 2, and then it is right now pi over 2 away from the 0 point. We're going to double that. Okay, let's transform this point. We're going to move it pi over 2. It is pi over 2 away from this 0 point, so we're going to double it. Okay. And what we have here, let's go ahead and move this point. We're going to move it pi over 2. It is pi over 3 away from it, so we're going to double it. And of course, we have that same relationship over here. And we can sort of extrapolate quite a bit. And what we get is something that looks like that, okay? So it has been moved over and then stretched from the x is equal to c, from the new 0 value. And that basically, you know, whereas this was the center of the graph, this is the new center of the graph. And like I said before, it's almost as if the phase shifts, the change in location, redefine your axes for you. So you have your real axes, you know, where x is equal to 0 and y is equal to 0. But then you have these new sort of functional axes which define 0 according to what's being done to the variable in that particular function. And so when we do horizontal changes in shape, remember that they have to happen with respect to my x is equal to c line. Alrighty, we're going to do another 2 on the next video, so be looking for those. Bye.